When we tried to train large language models locally across thousands of machines, we hit 3 fatal roadblocks. First, catastrophic interference. Standard federated averaging mathematically destroys updates when 2 local nodes learn conflicting information. The vectors literally collide and shatter. Second, behavioral forgetting. If we tune an LLM on simple JSON tool calls, the core language connections snap, destroying its conversational reasoning. And third, hardware limits. The Atom optimizer states instantly exceed the 8 GB VRAM limits of consumer GPUs. To solve this, we built the FOGR architecture, deployed natively inside the Ray's orchestrator. When a user asks a complex question, Ray's core doesn't just parse text. It dynamically executes deep OSINT tools like Spiderfoot and GeoSpy on the local machine. And this is our first major breakthrough. Instead of training the LLM to predict the next textual token using cross-entropy, FOGR captures the agent behavior as a directed acyclic graph. We use Wasserstein distance to minimize the latent gap between the query embedding and the successful execution path. We literally rewire the model's logic to favor successful OSINT investigations, leaving its English capabilities entirely untouched. To achieve this efficiently, we split the architecture. Fast local inference runs on GGUF. But background training uses a high-precision 4-bit QoRA Sapphire pipeline. We weave memory retrieval and graph reasoning into a single, unified PyTorch adapter. To mathematically guarantee that our new training doesn't immediately corrupt the base weights, we utilize SBZGA, a zero-gated adapter. At initialization, the alpha dial is locked at 0, enforcing a perfect identity mapping. We then parameterize the weights using the Cayley transform. This forces a matrix to remain strictly orthogonal, blocking gradient explosion, and maintaining absolute mathematical stability. To run this on consumer hardware without outer memory crashes, we exploit AMD IOCM zero-copy architecture. The massive 7 billion parameter base weights are frozen in standard system IAM. Only a tiny gradient flow enters the GPU during 5-minute background bursts. The raw OSINT data is instantly purged, and a tiny 15 megabyte encrypted matrix is generated. That encrypted delta weight is broadcast to our federated peer-to-peer network. Using secure hashkey discovery, thousands of decentralized OSINT clients form an ad hoc learning mesh around our enterprise host. But how do we aggregate thousands of updates without that catastrophic interference we saw at the beginning? Breakthrough number 2, server-side SVD allocation. When a client connects, the central server performs singular value decomposition, physically partitioning the model into independent, orthogonal vector spaces. Each client is restricted to learning only inside its assigned mathematical sector. When those updates arrive at the server, they undergo ties merging. The server filters out extreme noise and elects consensus signs. Because we strictly enforce orthogonal routing, the updates are guaranteed to be 90 degrees apart. We don't average them. We sum them. The updates stack perfectly onto the base model, non-destructively. The master model is consolidated instantly, without losing a single piece of local intelligence. That updated intelligence is redistributed as a shockwave across the globe. Every local client gets smarter. This is FOGR, a secure, continuous, decentralized intelligence loop that learns forever.